Murakaza neza bakunzi bacu kuri channel yacu Inkeri TV. Iyi ni channel twigiraho ibintu byinshi bitandukanye cyane cyane mu isomo ry'ubugenge physics. Nge ndi Teacher Meya. Nimba uri mushya kuri iyi channel, nagusaba gukanda kuri subscribe, kuri share ndetse uduhe na comment. So today we are going to see how to calculate the altitude of a mountain by using of a pressure, or how to calculate the height of a mountain by using what? By using of pressure or barometer. You have learned in geography. That the highest point, the highest altitude in Rwanda is Karisim with 4,507 meter. The highest mountain in Africa is Kilimanjaro with 5,895 meter, or 5,895 meter. The highest mountain on the world is Everest, Mount Everest, found in Himalaya, with 29,029 meter. So how to find that height? They say in geography they say the altitude is the height above sea level. Altitude is the height above sea level. What does it mean? If you have, let's say this is a mountain. Maybe this is a sea level. Here it is a sea level, and the height of mountain is there. So what is the altitude? Altitude, it is the height from sea level. If you come from the top of mountain up to the sea level, this is what we call the height, or what we call altitude. If you talk about the altitude of a point, it is the height above the sea level. If you measure the height of that point from sea level, that is what we call altitude of a point. So you can find the altitude of a point using pressure, using barometer. You know, barometer is an instrument used to measure atmospheric pressure. So you can use atmospheric pressure to find the height of a mountain. So before going in details, we have to know more about the Torricelli. We have to know more about the Torricelli barometer. What about Torricelli barometer? It is a barometer. Invented by Torricelli, as you see there. Torricelli barometer. Barometer, as how have said, it is an instrument used to measure atmospheric pressure. It has been invented by Evangelista Torricelli in that year. You are seeing it there. He took a tube of about 1 meter long filled with mercury of density. This is the density of mercury. You see it there, and place it vertically inverted in a mercury tube, as shown in the figure below. You are seeing the figure there. You see it, the figure there. That is the figure that Torricelli used to find the pressure by inverting the instrument called the barometer. We have a tube here which has 100 centimeter, or 1 meter, or 1000 millimeter, and then there is another tube there filled with mercury, and even the tube there was mercury. So what have he got as the result? He observed that the column of 76 centimeters of mercury above the free surface remained filled in the tube. What does it mean? As you say, this man Torricelli, he put a mercury in a vessel there, put the other mercury in a tube graduated in millimeter or in centimeter. It has 1,000 millimeter or 100 meter, means that it is a tube of 1 meter length. He put the mercury there up to the 100 centimeter, and then he inverted this tube into the vessel containing the mercury again. Of course, the mercury have to descend there into the vase, but they say he observed that at the column of 76 centimeter of mercury above the free surface, it remains filled in the tube. The mercury in the tube has not fallen into the vessel, or someone remains there up to 76 centimeters. So Torricelli concluded that in equilibrium, atmospheric pressure equals the pressure exerted by the mercury column. What is the cause for the mercury to remain there? If you put that vessel, we are here, if you put that tube inverted in a vessel, there is a mercury there. Why haven't all the mercury fallen down into the vessels? The mercury started to decrease, but when it reaches up to 76 centimeters, it remains there. What causes the mercury to remain there into the tube? It is the atmospheric pressure that pushing in the vessel. There is the atmospheric pressure there. There is the atmospheric pressure there. There is atmospheric pressure there, which are pushing into the vessel, and that atmospheric pressure, it is the one who caused this mercury to remain there. And by there, Torricelli has concluded that in equilibrium, atmospheric pressure equals the pressure exerted by the mercury column. Therefore, atmospheric pressure, you know how to find the pressure in fluid. Atmospheric pressure, which is equal to the density times the gravity times height. The man Torricelli has tried to convert that pressure find into Pascal, because Pascal, it is the NSI unit, international system unity of pressure. So how to find that pressure? We have seen that the mercury to remain there up to 76 centimeters, it is due to the pressure. How to find the pressure there? To find the pressure, as you have said, the pressure is equal to the density times the gravity times the height. So by using this formula, they try to find the pressure in Pascal. This, you have seen that this is the density of mercury. This is the height of mercury in the tube, 76 centimeters or 0.76 meter, and this is gravity. You can even use 9.81, and then by multiplying all those numbers, we will find that the atmospheric pressure is equal to 1.013 times 10 power 5 Pascal, and then this is given a new name. It is called the atmosphere. Atmosphere is another unity of what? It is another unity of pressure. You have to remember again, this experiment has been carried out on sea level. It has been carried out on sea level, means that if you move from sea level up to another point, the mercury will be reduced. The level of the mercury in the tube will be reduced. It will no longer be at 76 centimeters of mercury. It will be under 76. Means that the highest height of mercury in the tube, it is 76 centimeters of mercury at the sea level. As you go higher, atmospheric pressure decrease in the atmosphere. So by conclusion, if you are there, uh, 1 atmosphere, we have seen that there is another new unity of pressure called atmosphere. 1 atmosphere is equal to 0.76 millimeter or 76 centimeter or 760 millimeter of mercury. This is the millimeter of mercury, which is equal to 1.013 times 10 power 5 Pascal. This is this is the pressure found there at sea level. This pressure found there, Torricelli has give it a new name called the Torricelli. It is Torricelli, means that a Torricelli is another unit of pressure. Pressure has many units. We see that the pressure has many units, but you have to remember the SI unit of pressure is Pascal. But you have many units of pressure. It can be expressed in Newton by square meter. It can be expressed in Pascal. It can be expressed in bar. We see it can be expressed in atmosphere. It can be expressed in Torricelli. We have seen it. 1 Torricelli is equal to 1 millimeter of mercury, or it is equal to 133.32 Pascal. We will see how to find this Torricelli. Means that 1 Torricelli is equal to 1 millimeter of mercury, or it is equal to 133.32 Pascal. How to find this? How has Torricelli find this? Remember that we have seen that. We have seen that by doing experiment. Torricelli has found that the pressure there, the pressure in Pascal is equal to, let's say the pressure is equal to density times G times height. So by there we have seen that at sea level the height of mercury, this height is the height of mercury, and it means that even the density here will be the density of mercury and the gravity will not change. By there, by using this height, but at sea level we have seen that this height is equal to 70. It is equal to 76 what? 76 centimeter of mercury. It is equal to 76 centimeter of what? Centimeter of mercury. We have tried to convert this one into Pascal. I've said that the pressure will be equal to the density of mercury, which is equal to 13600 kilogram by meter per city. This gravity is equal to 9.81, and the height is equal to 76 centimeters. This 76, to be converted into Pascal, we have to change it into meter because the meter is SI unit of length. But what will happen if we don't convert this into centimeter, but we convert it into millimeter? If we change it into millimeter, we will find that the height is equal to 760 millimeter of mercury. We will find this one. The height there in millimeter will be equal to this one. So we are going to calculate the pressure by using the height, which is in millimeter. The pressure will be equal to the density 13600 times 9.81 times 760. This is a millimeter of mercury. So if we take this, if we calculate it, we will find that the pressure if we are using this one, we will find what? Let's do the calculation. Let's do the calculation. Someone to help us to find the calculation. We find that if you take the test of Markley, if you take the test of Markley, multiply by the gravity and multiply by the height of Markley, but it is in millimeter. We will find what? We will find 1300 times 9.81 times 760. It will be equal to what? It will be equal to, the pressure will be equal to 1,000,9,6,1,6,0,0. This is a pressure found using the height there, the height which is in millimeter. So means that is 760 millimeter of mercury. It is equal to this pressure. To find the equality between 1 millimeter of mercury, we should divide it by 7. We should divide by 76 and 0. What if we divide by this one? If we divide it by this one, we will find that the pressure. We will find that the pressure is equal to You can do it. You can do it yourself. Is equal to 1 C is equal to 1. Is equal to 1. This is C dot divide. You can divide. You can use it. You can do the calculation yourself. We will find what is there dot what have we found? Tell me, what have we found? Tell me what you have found. If you take the number there, if you take 1 1 1 1 0 1 3 9 6 1 6 0 and you divide by 760, you will find 133.44116. Means that 1 millimeter of mercury is equal to 133.410. Depending on calculation, depending on graph to use it, you can find in some books they write 133.332. It depends, but for calculation we'll find this one. Means that 1 millimeter of mercury is equal to that pressure in Pascal. So let's continue. This is what we will hear, how to find this one. We have seen how to find this one. We can use different ways. We can use different ways to find the pressure there, how it is equal 1 millimeter of mercury into Pascal. So another unit of pressure used in meteorology, they use a bar. Bar is another unit. It is mostly used in weather, in meteorology, and 1 bar is equal to 1 dot. It is equal to 1.013. It is equal to 1.0 times 10 power. It is 1.00 times 10 power 5 Pascal. and then you have seen that 1 atmosphere is equal to 1.013 bar. It is another unit. I think by now it is clear about how to measure atmospheric pressure using the instrument called the barometer, invented by Torricelli. If there is a question, you can ask it in a comment. You can write in a comment the question there, and then I will explain it for the next day. So, our topic today, we are going to see how to use that pressure. I have seen how to measure the pressure of a point. Maybe if you are at sea level, we have seen how this man called Torricelli has measured the pressure there, and he found that the pressure there it is equal to 76 centimeters of mercury. If you convert it into pressure, it is equal to 1.013 times 10 power 5 Pascal, which can be converted into many units: Torricelli, atmosphere, bar, and so many. This experiment, as I said, it has been carried out on sea level. And then what will happen if you go at another point which is not on sea level, at the mountain, at the head, at another point which has altitude which is greater than the altitude of sea level? You know that we consider the sea level as the zero. If we are going to measure the altitude of the height of a point, we consider the sea level as zero. If you come from zero there at sea level and you go on another point, as I say in the beginning, the highest point in Uganda is Karisimbi, the highest point in Africa is Kilimanjaro, and the highest point on the world is Everest. Everest has 29,029 meters of height or of altitude. How to find that altitude? We then go on the mountain and take a meter rule and measure up to the sea level. It is possible because let's say if this is the sea level, as I say, you have a mountain here. As I say, the height or the altitude, it is vertically from the top of the mountain up to the sea level vertically. They will not take a meter rule and measure from the top around and move around the mountain up to the sea. No, the altitude, it is the height. They take the height from the top of the mountain up to the sea level. Means that it is impossible to take a meter from the top of mountain and then go inside the mountain up to the sea level. So they use what? They use a barometer, they use pressure to find the height of a mountain. How? The principle there say, if maybe you have a mountain, as I say, you have here it is on sea level, this is the sea, here it is the sea level. They say you have a pressure here. We have seen how the pressure there is equal by using an experiment of Torricelli. If you take a barometer from the base, from the sea level up to the top, as I say, the pressure will decrease. It means that the pressure here at the base of mountain and the pressure there, they are somehow different. And as you go higher, the pressure decrease will not be increased. It means that the highest pressure you can find there it is 1.013 times 10 power 5 Pascal. If you go higher, it will be on that value. So the plans say that if you are going to measure maybe the height of a mountain, you will use pressure, because we say that the pressure, if you go there at the top of the mountain, the pressure will be decreased. What it does, it means the pressure at sea level, always it is equal to the pressure at the top of the mountain plus pressure of the air plus pressure of the air there. If we take the pressure, that will be shown by barometer at the sea level, we know it, and it will be equal to the pressure shown by barometer at the top of mountain plus the pressure of the air there. The same, for example, if we are going to measure maybe the height of this mountain from here, you are not going to start on sea level. let it call the base of the mountain. The pressure on the base, the pressure on the base, the pressure on the base of the mountain will again be equal to the pressure at the top plus the pressure of the air. Always the pressure at the lower level is equal to the pressure at another level which is high plus what? Plus the pressure of the air. This principle will be used to calculate the height of a mountain. We are going to see by doing some application. So let's go on application. I think you are there. Let's go on application. Here we have a question. Now I have a question. Read it clearly. The pressure at the base of the mountain is equal to 750 millimeter of mercury, and at the top is equal to 600 millimeter of mercury. So if the density of the air is 1.25 kilogram by meter per city, and the density of mercury is 13600 or 13,600 kilogram by meter per city, what is the height of the mountain? For here, we have a pressure at the base of the mountain. It's not on sea level. They give us the pressure on the base of the mountain, and they give us pressure at the top. The pressure are in millimeter of mercury, so they give us again the density of air and the density of mercury. So they want us to find the height of mountain. What is the height of mountain that have the pressure at the base, which is equal to this one, and the mountain that have the pressure at the top, which is equal to this one. As I say, if you see there, this is the pressure at the base, and this is the pressure at the top. The pressure at the top is less than the pressure at the base. It means that as you go higher, the pressure decreases. So we are going to see how to solve this problem, and all how to find the height of a mountain using what? Using pressure. So be attentive. Let's go. First, we have to look what are the data given. As you say, as you see it there, we have a pressure at the base of the mountain. We have a pressure here at the top of the mountain. We have the density of air, and we have the density of mercury. They give us 4 data. So we are going to have to use them to find the height of the mountain. So be there. If you are there, the data given, we have a C1, we have a pressure at the bottom or at the base. We have a pressure at the top. We have a density of air, and we have the density of mercury. Means that all data are well recorded. So we have many methods that we can use to solve this problem, or to find the solution, or to find the height of the mountain. The first method, as you have seen, they say the pressure, or I would say the pressure at the base is equal to the pressure at the top plus the pressure of the air plus the pressure of what? Of the air. We have seen it. So if you take pressure at the base minus pressure at the top, will be equal to the pressure of the air. If you take this one, pressure at the base minus pressure at the top, it will be equal to the pressure of the air. So pressure at the base minus pressure at the top, let it be called the pressure difference, or difference in pressure. Means that if you are there here, you have a pressure difference, or difference in pressure, which is equal to the pressure at the base minus pressure at the top. It is the first method that we are describing. So be there. They say that the pressure at the top, if you are there, remember, they say the pressure at the top, it is equal to the 750 millimeter of mercury. Pressure at the base is equal to 600 millimeter of mercury. So to find the difference, we will take 750 minus 600. We will find it. This way there. We will find it 150 millimeter of mercury, which is equal to 0.15 meter of mercury. If we convert it into meter, it will be equal to 0.15 meter of mercury. Means that the difference in pressure is equal to 0.15 meter of mercury. So let's convert this. This is the pressure, but the pressure expressed in millimeter of mercury. It is the height of mercury in the tube as we have seen on tertiary barometer. So we are going to convert it into Pascal, SI unity of pressure. To convert it, the pressure is equal to the density times gravity times the height. By there, we'll take the density of mercury times gravity times the height of mercury from there. So if you are going to convert it, be there, we will take the density of mercury. We'll take the density of mercury. This one is the density of mercury times gravity times height times the height of mercury. The difference we have seen there is 0.15, and then we use this height in meter because even Pascal is the NSI unity of Pascal. So we'll find this one. The answer is this one. You can do it yourself. You can do it, and then you will find this answer. So then after finding the difference, as you have said, this pressure difference is equal to the pressure of the air there, and the pressure of the air, always the pressure of a fluid is equal to the density of that fluid times gravity times the height. So by there we will find that if we take the density of the air, this is the density of the air, you see it there, times the gravity times the height will be equal to the pressure difference that we have found there by using the principle that we have seen above. So this height is the height of mountain. It is that one which is asked in the question. The h there, if the h there in pressure of air, the height there, it is the height of mountain. Means that if you take the density of air times gravity times height, this is the height of mountain, will be equal to the change in pressure, the pressure at the base of the mountain and the pressure at the top, but they have to be converted into Pascal. So let's continue. We will find that if you calculate for h, you will find that h will be equal to this one over this, and we find that h is equal to 1631.999 meter. We can round off, and then to become 1632 meter. This is the height of the mountain asked today. This is the height of what? Of mountain asked there. This is the height. It is the first method. As you have said, we have many methods. Let's see the second one. Let's go on the second one. The second one, again, we will calculate the pressure difference. We will find the pressure difference, but the pressure here will still be in millimeter of mercury. We will find it 150 millimeter of mercury. We have seen it, and then we have even seen how to convert this into Pascal. We have seen that 1 millimeter of mercury is equal to 133.416 Pascal. We have seen how to calculate this, and then if 1 millimeter of mercury is equal to this Pascal, we can directly change this millimeter of mercury into Pascal by multiplying here by 150. That is what we have done here. To find the pressure difference in Pascal, we take this pressure difference, which is equal to 150 millimeter times this one, because 1 millimeter of mercury is equal to this Pascal. If we multiply this, we will find the same value as the pressure difference in first method. So after finding this one, always this pressure difference, always this pressure difference will be equal to the pressure of the air. So we will equalize this one with the density of air times gravity times h, and then the h there always will be will be the height of a mountain. So you will find the same height of a mountain, 1,632 and 32 meters as you have seen in first method. We have even third method. For the third method, convert each pressure into Pascal. We have seen that the pressure at the base it is equal to 750 millimeter. Convert it into meter, it will be 0.750 millimeter times the gravity times density of Mercury. Means that the pressure found here, I think here, this is the pressure at the base of the mountain, but expressed in Pascal. The pressure at the top will be calculated in the same way. You will take the density of Mercury times gravity times the height of Mercury there. The height of Mercury there, it is 600 millimeter. Converted into meter, it is 0.6 meter of Mercury. So the pressure found here, it is again the pressure at the top of mountain expressed in Pascal. So we are going to find the pressure difference. We are going to find the pressure difference. The pressure difference will be calculated in Pascal, of course. We will take the pressure at the top, you see it there, minus pressure, no, sorry, we will take the pressure at the base minus pressure at the top. If we take the pressure at the base minus pressure at the top, we will find again 20,012.4 Pascal. The same answer as the answer found in the first method, second method, even the third method. If you use this method, you will find the same difference in pressure. And again, this pressure difference will be equal to the pressure of the air. Density of air times gravity times height. The height there, remember, as I say, the height there is the height of the mountain. So if you find or if you calculate the height, you will find again the same answer as in the first method. You will find 1,000. Sorry, you will find 1,632 meter. For all the methods, if the pressure difference are the same, and we say the pressure difference is equal to the pressure of the air, and for the air the density will be the same for all methods. The gravity will be the same, and even the height will be the same because we are calculating the same height. So means that for each method you will find the same height of the mountain. So thank you to be with us. As I say, you can press the subscribe if you are new on this channel. You can press share. You can send us the comment telling us how you have seen the content there, what we can prepare for you for the next step, and even the comment can even give us the comment which motivate us to continue. So thank you to follow this listening. Let's be together in the next one. Nkuko nabibabwiye rero, iri ni isomo rya mbere dutanze. Watwandikira ukatwoherereza kubyumva. Uko niba uri mushya, kanda subscribe, kanda share, uduhe comment, tubwire uko wabibonye, icyo twahindura, icyo twakongeramo, ndetse n'icyo wifuza ko twagutegurira mu isomo ry'ubutaha. Ciao ciao, bye, we are together. Iyi channel nkuko nabibabwiye yitwa Inkeri TV. Njyewe ndi Teacher Meya, ndabakunda, bye.